Uh, Today's my talk is titled "What are states of consciousness?" The main subject of this talk is the notion of state. The state is a very usual term in English. Everyone uses this term, but I have never heard the definition of state from other researchers. Because I am a mathematical physicist, the notion of state is most, how to say, the technical word, technical term in our field. From this viewpoint, the rethinking of the states of the consciousness will be very fruitful from my intuition. So I will introduce a notion of state in the mathematics called non-commutative probability, and unite that concepts to the category, which is one very big issue in our Qualia structure. So let's start. This is one-page self-introduction of me. As I said, I'm a professional on the quantum field, mathematical physicist. Maybe many of them or some of them know about the quantum fields. Quantum fields in Japanese, ryoshiba, is roughly speaking and historically speaking, the unification of the relativity theory, Einstein's relativity, and quantum theory, the two of the biggest revolution in the 20th century physics. But of course, also not only relativity theory, but also some condensed matter physics, or many kind of non-relativistic context is also important, but it can be considered as a transformed version of the relativity structure. So roughly speaking, quantum field theory is nothing but the unification of relativity theory and quantum theory. But it is one of the hardest problem, maybe easier than the hard problem, but the hardest problem in the mathematics and the physics. Because this unification of relativity theory and quantum theory is very, very mysteriously, it seems impossible to unify these things. And there is many, many no-go theorems. If you accept some axioms of relativity theory and some axiom about the quantum theory, then we have only free field. That is, there is no interaction. No interesting things occur. This kind of no-go theorem is known. So we should make the revolution of the thinking, the third revolution. So as a mathematician, I think the most of people, if they confront a difficult question, the most of people do that to think the easier problem or special problem than the original problem. But interestingly, in mathematics, the converse is often true. To prove something, generalize it, to unify something, to generalize it. So we can consider the category theory as a kind of generalization of the relativity theory. Why? Maybe many of them knows about relativity theory. It is some kind of the theory of transformation. The one inertial system, the another inertial system, and these observers has different values of something and different values of something. But it is not the contradiction. There is a very coherent transformation structure. As the first they now use the terms, and maybe Steve also, the coherent deviation notion, which can be incorporated with category theory, which is called natural transformation. So the relativity theory is something like the functor and the natural transformation theory. The observers, taking some coordinates or inertial system is choosing some representation. Representation is in category theory is generalized to the notion of the functor, as Nao and Steve introduced already. And the transformation and coherence between these different representation is modeled by natural transformation. So the Lorentz transformation or Poincare transformation in relativity theory is generalized to this kind of natural system of natural transformation. In other words, the category of functors and natural transformations. Of course, this is a picture of categories, and this is object, and these arrows are arrows. But many interesting category is composed of object as functors, the arrows as natural transformation, which is called the functor category. And also interestingly, any arbitrary category can be embedded into this kind of category, functor category. This is called Yoneda embedding. Okay, so maybe you can grasp some feeling about relativity theory and the category theory. Then let's go to the quantum region. Okay, what is the mathematical generalization of quantum theory? The answer is this. The notion of algebra and the states. This has a rigorous definition, so I will introduce later. But let's consider the quantum theory. What is a revolution quantum theory? This is a very general, the vast generalization of classical probability theory based on the measure theory and some kind of notion of probability space. To explore, to explain the notion of probability space in usual term is maybe this kind of description that there is many possibilities here, and this is a space of possibilities. And there is a weight called probability, which corresponds to the subset of these kind of possibilities. This is very naive, easy to understand, but quantum theory violates this kind of thing. There is no such a probability space to describe this kind of quantum phenomenon. It is known, the quantum theory and classical probability theory in the level of theory, it's contradicted. It is known from the von Neumann or the other colleagues, but it took long time to verify that this reality violates classical probability theory. This is this year's Nobel Physics Prize, the violation of the Bell inequality, which does not depend on the specific theory of the quantum model. It forces to go beyond the classical probability theory. So this is non-commutative probability space. That means that there is some kind of the system of quantities called algebra, and mapping from this algebra to some, in the quantum theory, this is a complex number, but many kind of candidates here. But the point is this phi mapping, which maps each physical quantity into the expectation value, is the most important ingredient in the non-commutative probability theory. So I will introduce more detailed version of this explanation later. But the point is, we should move to the unification of category and algebra and states, non-commutative probability. I unified this 1 year ago. So I will make some introduction to that. Then I realized the original motivation is to go beyond toward the quantum fields, but I also realized this is useful to this Qualia structure. So this consciousness means such kind of thing. Okay.
Just
okay.
So relativity theory and the quantum theory as original can be directly going to unify into quantum field because of the normal theorem and so on. But if each of them are generalized
yes.
some way, then
yes.
they maybe.
Yeah, that's kind of. The main point is in relativity theory, the essence of relativity theory is conserved, but the formulation, like a space-time is considered as a set of points. But my idea is to replace the notion of space-time into the not set of the points, events, to the category of the event ties, event relations, processes. This is very simple generalization, but then it comes the non-commutativity very naturally. And I think this is a key to the investigation of consciousness. And then why, for example, the quantum cognition structure is interesting also. So let's get into the contents. So we begin with a very general thing, the general theory of system and dynamics, not only the quantum fields, not only the consciousness. If you make some physical or scientific theory, we need the notion of system or the dynamics or something. This is very affected by my ex-supervisor Ojima, who is a physicist, who uses the term the micro-macro duality. It's very surprisingly, this kind of thing is Tanichu-san's talk also related to that kind of talk. But what is system? System is all, of course, some subsystem of this world is system, but system is not isolated to other side of world. The environment is also subsystem of the world, which is very closely interact to this system. Then, this is of course some pragmatic framework, and I don't say that there is a substance of the system and the environment as system. Of course, it is some kind of pragmatic distinction. So you can change this distinction in context. For example, we can think of this as the system and this as the environment, but also we can think of this room itself, the system, and the other outside of the environment or something. And even in this case, like this, the molecule of water is a system, and the other, this is the environment or something. So you can think of what is system or what is environment can have the different meaning. But pragmatically, we focus on some system and the other environment. So the point is the system, structure of system or property of system of something, so-called intrinsic property is model in terms of algebra, because all the science which is not only qualitative but quantitative nature needs some calculation structure, needs some the algebraic, that means plus, times, or something. Without that, we can, as far as we can test any kind of test or check something. Of course, statistics also. But this is related to the systems in inner like Steve used the term inner and outer. The inner structure of something is in mathematical physics is represented as some kind of algebra. Like every electron has some kind of the property called spin or position, or momentum, or something. But it varies in many different environments or the protocols of experiment. Then it differs from it is position, momentum. This is some kind of the algebra. You know about X, Y, Z, the data, which is called in modern mathematics, it is called indeterminate, not determinate. So this is not have specific values. That X that grow indeterminate thing. This is called the algebra, X, Y, Z, or something. Then, after that, by changing and determining the relationship between the inner system and the outer system, then we have some expectation, evaluation. So this system and environment relationship between system and the environment is modeled as a state which will be defined later. So this is an inner structure. This is relationship with the environment. Then, but of course we can think of that this algebra and state is not isolated things. It should be reflect some kind of dynamics, basic structure of dynamics, because these relationship varies in time, of course. This kind of dynamical structure should be, for example, for quantum field theory, the space-time structure should be reflect to this kind of thing. So the question is, how to make algebra and how to make state from this structure. This is the modeling system and dynamics by category algebra, which is algebra reflecting the structure of the category and the state of category. This is sometimes useful terminology. This should be called a state on category algebra. But from my theorem, this abuse is sometimes justified. So this is the overview of this talk. Okay, algebra and state. Let's some definition. Of course, not mathematically oriented people just hear and forget. So forget by bias. This what algebra. What is the observable in the case of the quantum theory, the algebra observable such as momentum, energy, or something, which are a spin in the system with finite degrees of freedom. It can be represented as matrix algebra or something. And if you are familiar with quantum mechanics, there is a very important operation called addition and multiplication of matrices and scalar multiplication and Hermite conjugation. Hermite conjugation is some kind of generalization, complex conjugation, which is very necessary to define notion of positivity, which is very important in many of areas. So here the algebra means the star algebra. Over in the quantum theory, the star leaf is C, complex numbers, but we can change this notion more generally. If you are familiar with modern mathematics, this ring is very strange. Ring, the notion of ring is very famous. This is the system with addition, multiplication. This is a ring. And also the negatives. But so ring is a kind of joke ring without negatives. Negative is n. So weak minus n is a ring. It is called also semi-ring. And some kind of people like tropical, maybe heard about tropical algebra. It's a max plus algebra or something. This is not ring, but ring. So you can use this framework with some kind of regulating the cost performance to maximize or minimize something. This kind of optimization problem is also in this framework. Okay, so this is scalar, like complex numbers or real numbers or tropical numbers or something. So the point is, before the quantum theory, essentially speaking, only the commutative algebra is needed for the description of nature. And today, Tanichi-san talked about Charles Fondler's part, and he himself and his brother is very pioneer of non-commutative algebra theory. But in that year, it is just amusing technique. It's not so much useful. But after the quantum theory is found, this becomes a very important, essential thing. So roughly speaking, the commutative is classical, non-commutative is quantum from the mathematical side. And nevertheless, if we ignore this point, almost all the theory is concept from the jumping from classical to quantum. So almost all people think that there is two theories, classical physics and quantum physics. This is divided, but it is not true. In this sense, quantum theory is a generalization of classical theory, because non-commutative is a generalization of the commutative. But of course, quantum physics is some branch of non-commutative theory. So I talked about the non-commutative theory, which contains usual quantum theory as a sub-branch. Then, what is a state? State is an expectation function. That means for each, for example, A, this is algebra, like this is momentum or position or the square momentum or the variance or something. Variance, sorry, square of momentum or something. But so that kind of quantity should have the expectation value. Then assigning expectation value is considered as a linear. Like for the random variable case, the classical case, the expectation value is linear. It is very famous because it is just averaging. So it is very natural to think that this expectation function should satisfy the linearity. And in classical probability, the total probability is 1. This is the starting point of classical probability. It is extended to this notion. 1, this is like a random variable. That value is always 1, like thing is expectation is of course 1. And also the probability should be positive. This is correspond to this, and this is expectation that is positive. So state the notion is mapping from algebra which satisfies the linearity, unitarity means this, and positivity. This is all. This is a 10 minutes introduction to quantum theory. No need. Maybe you have heard about the Hilbert space or something, eigenvalue or something. Everything comes from this. No assumption. This is well-known fact in quantum field, algebraic quantum field theory, but other field, this is quite unfamiliar thing, I think. Okay, then this is always known, but here my introduction to my work, I unified or I make some general scheme from starting from category theory to the non-commutative probability theory. So what is category? But category, because now and Steve did the greatest introduction to category theory, so I can assume what you know where about what category is. But the image itself is some kind of category, is a mathematical system consisting of something called object and arrows. Objects like this, and arrows like this. The frequently asked question is, what kind of things can be considered as objects? What kind of things are considered as arrows? The answer, anything, everything. You can choose. The point is, whatever you choose, it should satisfy that arrows has the codomain and the domain. So starting point, the end point should be defined. And also, so this axiom is called directed graph. But the category has a more rich structure called composition. You can compose the new arrows from this kind of pairs of settings. And this composition should satisfy this associativity law. And Steve also stressed that, very interestingly, this axiom is very useful, that for all objects, there is the one arrow called identity X, which do nothing. This do nothing arrow do very important work. And I can say that one thing, that by this axiom, we can prove that this identity is, the axiom says that exists such a thing, but this existence also implies the uniqueness of this. So you can consider the object as mere representative of identity X. So in that sense, the category is the system of arrows. Object is just a special kind of arrows, which is called identity arrows. Okay. Then, how to model? This is some kind of very ideal framework for the dynamics, but how to model actual dynamics is a real problem. As I said, the system is represented as algebra, and the environment is represented by state. So the state, what is the dynamics? Then, of course, the time change, the series of the flow of the states. For example, the just waiting something in quantum theory is represented by this kind of so-called unitary evolution. But how to construct this algebra and state from category? As a formulation, it is good to put algebra and state as starting point setups like quantum theory. However, in the concrete modeling, algebra and states should be constructed from some basic structure of dynamics, especially in consciousness studies, because there is no, how to say, no good algebras in the consciousness theories. We should construct from the data or something. We should make something like Heisenberg did for the quantum theory. If you're interested, I can say much things about the finding quantum theory, but I omit here. But the answer is category algebra states on category. So how to make the algebra from the category? That is called category algebra. Category algebra is algebra which consisting of some kind of function, some kind of function satisfying some piloted condition, but it is just a technical detail I omit. The point is, this category algebra is consisting of some kind of functions on arrows, like some kind of the coefficients. You can think of x, y, z, then you can think of 2x minus 3y plus 5z. So this kind called the linear computation. Or such kind you can make a polynomials or something. So the point is some letters can be linearly combinated. So this linear combination of this kind of thing is elements of the category algebra. The sum is very straightforward. The point is multiplication. It is defined as follows, but do not try to memorize. The point is, if you are familiar with, for example, the machine learning or something, there is a very important operation called convolution. Well, convolution is in the Fourier transformation context, it is also important. And if you are familiar with linear algebra, the matrix multiplication is convolution. So almost all useful so-called multiplication comes from this convolution. Then this definition, very simple, but is generalism, which all the example I said. Then, interestingly, it has units. That is, for object or identity arrows, it has a value 1, or other arrows, it has a value 0. This simple thing becomes a unit. Unit means do nothing for the multiplication, like a generalization of the number 1. Okay, so dynamics can be represented as a category consisting of possible processes. So object is possible events. For example, quantum field, the space-time, the object of space-time events. And arrows is a possible processes. Maybe it can be virtual, like a time reversal movement of electron, which is called positive electron, positron. But sorry, how to say the positron というか陽電子ですね、陽電子。But some kind of thing. But this example, I think you are familiar with this category. Like, for example, the spike of each neurons or some region, as coarse grained region of spikes, can be considered as objects. And if there is some causal relationship, then it becomes arrow. But to make the category, we allow the not direct, but also indirect causal relation should be counted as a causal relation. But the point is, this causal relation does not necessarily satisfy the deterministic property. Of course, it is statistical, okay. And the point is, this side of without a NOV type, some people call this is counterfactual nature or something, but this point is quite important. But anyway, we can construct this kind of category as a framework of the possible dynamics. So what is the algebra, category algebra? But first, we should say that category algebra includes category. We can make category algebra from category, but the original category can be embedded in the category algebra. So it is some kind of extended version of category. In what sense extended? This is some kind of category gives a qualitative structure, then plus R, the rig is quantitative nature. So quantitative structure based on qualitative structure is this category algebra. And the example, so in that sense, every arrow can be considered as a special element of category algebra. So we identify this. So this is a demonstration of the operation category algebra. This is very little, pretty category. This is F, this is identity, this is another identity. So 3 arrows, very little, pretty one. But considering this category algebra on this category is that the elements of category algebra is some kind of linear combination of arrows. That linear combination is this kind of 2i plus f plus 3j or 3j or something. But the operation is easier than the original high school algebra. It is easier than high school algebra, and I can say that we can do some kind of mark sheet. なんていうの、センター試験に当たるのってなんていうんだっけ、multiple choice program to the some examination. You can I can imagine the high school students solve this category algebra problem. This is just for the usual distributive law, but for example, 2i minus 4i becomes minus 8i because identity and identity becomes identity. But if you consider 2i, 5f becomes 0. It means this is an order is usual functional composition. Then this, for example, I and f. If I followed by f is okay, but f follows by I is not compositional. So in that case, it vanishes. So that intuitionally, the connected arrow can be composed, but these kind of things or these kind of things vanish. So the non-connectivity is has a reflects the structure of this category algebra. So it's a kind of very sparse. And this kind of operation, we have the almost the same or easier calculation in high school algebra, but non-commutative. The AB logical video. Actually, if there is only one means at least one arrows which links the different objects, then the category algebra is necessarily non-commutative. So if the things, entities, it has some intrinsic relationship, then the non-commutativity is quite naturally arises. And when commutativity holds is, for example, this type of category called monoids, that is, there is only one object, then the category algebra can be commutative, not always, but can be commutative, which is called polynomial algebra, which is high school algebra. And if you are familiar with group theory, the group ring is if the group is commutative, then group algebra is commutative, or the set, which is also called a discrete category. That means the set is the only object, no arrows, such kind of thing. So the arrows is all identity arrows, no non-trivial link between them. Then this category algebra coincides with this function algebra, which is typical algebra. Then, as an example of non-commutative algebra, I think most of the people learn the matrix algebra first, maybe. But it is not an accident. From the category algebra viewpoint, every category algebra, surprisingly, if the object is infinitely many, continuously many, or the arrows more and more many, we can define category algebra and have some matrix algebra-like form. Of course, for the empirical study, we don't need such a thing. But the point is, category algebra can be considered as a generalized version of the matrix algebra. So the notion of column, row, and the component can be defined as follows. But this is each each components, you know the components. 要するに成分ですね。So the components, each component, usual matrix has as a matrix elements, components, only one number. But in the category algebra, this is some kind of linear combination of arrow comes like a polynomial. The elements in category algebra can be represented as infinitely many. If the object is infinite, then infinite many column and row matrix. It seems very terrible thing, but the multiplication or something is very naturally defined, well defined. So the convolution becomes the matrix multiplication, and this kind of linear algebra formula is conserved. And if we consider the simple graph, symmetric graph, then the category algebra becomes usual matrix algebra. So it is a generalization matrix algebra. Then maybe you can, okay.
Can this be described as tensor?
Sorry?
Can this be described as a tensor, not a matrix?
Tensor, yeah, matrix can be considered as a tensor. So of course, this is also tensor. And maybe this question, if we consider some set of components, then there is some matrix, the sub-matrix. This system of sub-matrix forms a tensor category. So I think that your intuition is correct. So this is intrinsically have some of the tensor productive structure. So maybe you can think of the if okay.
Just so this category like matrix that also encodes connectivity.
Yeah.
Right. Like let's say if the one thing is connected to this in this way, then the entry to top right is there, but not on the so in the kind of tensorial representation, only means that the network that is represented by this thing can be composed into two independent parts.
Like if the arrows has called this kind of, for example, then there's some kind of 2, 1, 10, 1, 2 tensor. Like yes. Then maybe you can say, oh, I know about that such kind of connectivity concepts in the network theory for the consciousness or something. But yes, but there is an important difference from the traditional network theory. Because network theory focuses on just the existence of connection. So the multiplicity of the connection is all, as far as I know, in the application, especially the application of the consciousness study, ignored. What I say is the definition of category allows the many paths from this to this. But usual network theory makes simple this kind by using the fixed weight for this multiple thing. What worse is if there is a loop, this kind of procedure neglect the effective loop. But I believe every neuroscientist or consciousness study researcher agree that the loop is essential. So the one merit to model the neural structure or something is this between two, there can be the multiple arrows or loops. And also this, as you understand, arrows are some kind of indeterminate. So X or Y or Z, there is no fixed value. So by changing the environment, this X, Y, Z value should change. So if X, Y, Z structure is given, this is very useful. Like consider if you do not use X, Y, Z, how it is difficult to calculate the universal formula. 2 plus 3 equals 5, like 7 plus 3 is 10 or something. But you can think of X plus Y. Then this situation can be unified in one relation. Then in algebra, we can think of the substitution that X, then X to 2 or Y to 0.3 or something. This is given by state for the category algebra. So what is state on category? We can construct a star algebra. Technically, if C is a Dagger category, but Dagger category is quite a general notion category. So not so strong constraint. But then we have the star algebra from category as basic possible structure of dynamics. And for any small category, it becomes unital. Then this is unital star algebra. Then it is basis for the non-commutative probability theory on categories. Then we can define state as linear function as we defined before. But the theorem I proved assure that defining state in the meaning of expectation function that is very abstract. Very abstract like this. State, the notion of the state is quite abstract. The arbitrary map will satisfy this is called state. But I think that this very abstract thing has concrete form, one-to-one concrete form on categories. That is just certain weight on arrows. That it means, yeah, this is very nice, so I surprised. But because the arbitrary state can be represented as like a category algebra levels, we can think of this as indeterminate, like 2f plus 3g minus h or something, this kind of thing. But state, to define state is to define each arrow to the some value, like 0.3 or minus 0.2, or this becomes 10. So assigning arbitrarily that this number is just the defined state under converses. So my idea is that then technically, if this kind of state is given by famous GNS construction, we can reconstruct the Hilbert space. If you don't know, just forget. But it is quite useful to not only the quantum theory, but also the machine learning or something.
Probably, I guess, judging from the expression, I guess some people probably got lost about this state as a weight on arrows. And I think because you kind of made a very concrete kind of example of that neuron-like structure with the firing and different commands, they have that idea. And then on that, when you talk about the state, probably many people will probably imagine it's a measurement of that neural state or something like that. But when you start to say that assign this 0.3 or 0.2, it doesn't feel that at all. Okay, yeah, that's this example is what I said, what I saw. That, for example, Oizumi-san spoke. You make the Bicenter. Why?
So the neural structure is quite full of noise. My idea is the point is expectation. So what is corresponding to the quantum state is not the one-time strength, but expectation. Then this weight is just for this stated non-quantitative category algebra.
Then, yeah, in our terminology, then it probably corresponds to higher grade or
Yes.
sometime.
Yeah. Then it's for sometime and so
which could
yeah, some kind of time basic time scale for the basic time scale. I see. Yeah.
And that's the state.
Yes, yes. So just to clear the discussion, that my work is from general category, which is most general notion category, we can construct category algebra, and non-commutative algebra and state is of course very arbitrary. But if this non-commutative algebra comes from the category and as a category algebra, then state has a concrete form. Especially if the neural network like category, then this is quite concrete. This is my idea. Then, what are states of consciousness? My idea, this is of course hypothetical. Individual spikes of neuron? No, of course not. System of possible process, good, not bad, but unsatisfactory. Because if this is so, the change of the consciousness cannot be described. My hypothetical answer is a state on the category, spike and causal relations. So this is the brain, our information, Oizumi-san's notion of information structure, like from brain, but brain causal relation is important.
It's like activity.
Yeah. That's the kind. So this is some kind of information structure I've seen. Then based on this is the system intrinsic, but environment change. There are stimuli or something. Then this causal strength of causal relation, of course, change. Of course, very rapidly it's changed. The point is this corresponds to the average expectation for the specific time scale. I think this intuition is can be agreed with experimentalists also. So this answer, of course, the hypothetical seems natural or almost trivial, but important thing is there's haven't been mathematical counterpart. So I think that the point is the higher way. But the point is we should consider the loops or multiples. So generalized kind of finite way. Makes sense.
I finally kind of like got the why do you think that the multiple pathways in I don't know. My interpretation is that if you want to make a sort of simple analysis, like network connectivity, or let's say a space of 1, 2, and 3, or 3 pathways, you probably usually average it, right? Or take the mean of 3 pathways. But what the cyber is saying is that if firing rate of the first path is 1, and the firing rate of the second path is 0, and the third pathway is 3, then that might actually correspond to different conscious experience. First path 0, second path 3, third path 5, right?
Yes.
Yeah, good. Excellent. That's correct.
That's correct. I think this is the answer. but the point is.
And that's also consistent with the IAT.
Yes. Exactly. So I believe that consciousness researchers, good consciousness researchers, we agree with intuitive And that's I know, I see. But the point is there is no mathematical counterpart for that. Okay. This is my. So then, if there is a mathematical counterpart to the modeling, the actual dynamics is not the dream. So as it is some kind of generalization matrix algebra, so you can think of generalized kind of unitary thing or the dynamics. Dynamics as a some kind of sequence of the state as a linear function or weight, multiple weight or something. Then this is represented as a quantum version of randomness. Randomness is very familiar with Makiko and colleagues. So quantum cognition people uses this quantum work. But from my viewpoint, it is very mysterious. Why this cognitive process can be represented by the operators on the Hilbert space. But this is not a mystery from the category of algebra side. Because this is non-commutative probability and state is if such a thing, the algebra and state gives Hilbert space. And each algebra element can be represented by the operators on the Hilbert. That's Hilbert. This is mathematical. So if you admit the state is such kind of expectation function, then why Hilbert space methods is important or is effective is no mistake. So more generally, we have irreversible dynamics like quantum measurement, like thing. Of course, I believe there's many things that the irreversible thing like. So of course, not only the unitary-like thing. So this is almost a summary. There are new way toward your so-called hard problem. It is like a joke, but including me, it is very hard to consider like comparing different subjects. Of course, we do some work break such wall, but I think this idea is also related to the thing. C and C prime from some kind of quotient. Quotient means the quotient rate, like the higher scale. And then we have some categories of maybe different. So if you want to connect it directly, maybe it's difficult. But considering the category algebra, and category algebra has notion state, but this state as function, the abstract thing is by my theorem, one-to-one corresponding to the positive function of arrows that multiple version of that. I think you can observe, you can check. Then if this numerical data is given, this is given. Then you can construct the convenient Hilbert space or something. And the point is, this is represented by some kind of transformation between the positive semi-definite matrix, a general time. So, by GNS construction, we can think of this as space operator. Then we have the von Neumann entropy or algebraic entropy, or this is related to the operator algebra. And positive function is gives kernel, positive kernel. Positive kernel gives a reproducing kernel Hilbert space. So this is just a short way to the math line. So learning robotics or something can be connected to the quantum information or the quantum physics. And this alpha corresponding to state change alpha is in general not star homomorphism, but CP map, completely positive map. Physics generalizes on the star homomorphism state. Then it will naturally point to the quantum cognition quantum model. So the sameness of Qualia, the more what is the sameness? To check the sameness of Qualia is checking the existence of this invertible correspondence between the metrics-like things. And I believe this is very closely related to all these work. So the similar thing to the such expectation value of the strength for the multiple paths. So summary is here. The brain phenomena should be considered some kind of category of spikes or causality. The observable of consciousness is category algebra. States of consciousness states on category. The flow of consciousness, a sequence of flow of states on category, such as quantum walk, a new way towards hard problem. So thank you for your patience. Longest talk, maybe.
Okay. Question? Comment? Yeah. You are saying that so the state of consciousness is state category. But here you assume that consciousness is generated by neural activity. And so it's like you are saying that the dynamics of neural activity themselves should be described by quantum mathematics or non-commutative.
Oh, that's a very good question. First of all, I said that this quotient of this quotient of means actually the raw activities brain, not just the raw activity brain, but information structure. This is what I intend now. But for that type of category, if you want to analyze the fully do the full analysis on that, then you need non-commutative theory naturally. Because, for example, there is a very famous field called random matrices. Random matrices is actually a branch of non-commutative theory. But the early stage of the research, they consider only one matrix. Only one matrix. But even in non-commutative algebra, if you focus on the only one algebra like A and A squared with A to 3 is commutative. But in general, if the algebra is non-commutative, but if you focus on only one algebra generated by only one element, it's no problem. So random matrix research begin with classical paradigm, and it is okay. But if you can consider essentially different matrices and relation between them, then we need. But if you do not have such a viewpoint, they see the matrix, but they don't see how to evaluate the relationship with AD. So if you want to describe and study these non-trivial relations between these matrices, then we need non-commutative. The same thing should be in consciousness studies.
Right. So I mean, you and Nara and Makito now investigating the quantum cognition thing, and your theory can explain quantum cognition thing in human behavior.
Yes.
Like you are trying to explain that from the sort of neural dynamics level.
Yeah.
Or that's your intention.
Neural dynamics, or more precisely, information structure.
I see.
Because it is how to say the related to the meaning of expectation value. Why expectation? This is the question from you now yesterday, a very important question. But the point is, this kind of time scale program is very important. Then some course grading is essential. It doesn't mean that course grading is just approximation. It is a very physical one. Okay. So, like Harkin's principle on slavery, within the complex system, in Tanish's and spoke, individual, social, in context, there is a very powerful scale arises. Then the main scale, coarser and higher, is suppressed. I think the exclusion principle in the IIT reflects such a thing. So coarse grading and multiple level creation makes some most powerful scale. Then given this powerful scale, we can have a well-defined notion of expectation value or something. Then I think that this is a correspondence mathematical counterpart for the state of consciousness, not the state of brain, the state of course.
Any other comments?
Yeah, maybe just a high level question or understand how to answer so yeah, I guess the basic word is you have this sameness of Qualia. But can you also look at the similarity of Qualia as well?
Yeah, as well. Yes. Some kind of this is just another, so we can skip to the story. But if the matrix seems very different, but if these matrices are conjugate, that means you can multiply something, then A becomes B by the invertible matrices. Then it is essentially the same, like diagonalization, Jordan form, something. So these are essentially. But if there is no such invertible matrices, we can consider the pseudo inverse, quasi inverse, or something. So this is related to some similarity stage. This is not essentially the same, but very same, similar. So by using the quasi inverse, we have some kind of distance, the most good approximation. So I believe it.
I think that's actually a really interesting idea. So probably by default, we probably think about if this algebra is a state of consciousness of Qualia, we want to take a distance between these two things, right? That's what you have in your mind. But what Saigo-san was saying is that if there isn't some kind of matrix, like B or whatever, B conjugate or something like that, that makes this into A prime, then this and this is essentially the same. So in this case, this must be the same. Even though this as a matrix, it looks kind of different.
Yeah.
I don't think we have never considered this type of similarity, but that's actually
related to always sounds well. So Gromov, the idea is such kind generalization, grid rotation or something. So so that is the sense. So this is that shape, another shape, different by translation. But if you rotate or then that kind of thing can be considered as matrix conjugation. Then I think, of course, this matrix conjugation does not always hold. So in that sense, because there is no inverse matrix. But in that case, or even in that case, I think that dagger, I said dagger category. Dagger category is generalization viewpoint. Viewpoint means that every arrow is inverse. The dagger category does not need this inversion. Weak inversion, sometimes approximate inverse or something.
I wonder if this kind of similarity is the kind of similarity of which we find in obviously different thing, but similar.
Yeah,
Like
yeah.
experiment where
Yes.
as a the thing patch, it's obviously different between the two, but when you ask similarity, then if the patch contains human face, they are rated as similar kind of thing.
So maybe this in simple case, the Qualia maybe appeared as an index of Qualia, maybe appeared as some like eigenvalue of the matrix, invariance, like our idea is redness or blueness or something is not the isolated thing. The shape, the shape means these things or relation itself is some kind of Qualia. That is mathematically completely analogous to the idea of the eigenvalue. Like quantum mechanics also. All the quantum mechanics is related to such a kind of notation, like representation or such kind of thing, which is interestingly related to the idea of relativity theory also. So by generalization to the category, then we have non-quantitative probability space. So all these actors comes in, enter. So just to begin the theater.
Any other comments? Question? Fine. Yeah, of course it can continue.
Yeah. Sure.
So, yeah, thank you.
Thank you very much.